Okay, so hi, we're from the Thermal Reticulations group, and my name is Alexander Peña, Camille Charadin, and Manny Williams, and we're pretty much going to run through the what we've been doing for the last 4 days and what we've been doing also before we arrived here. So when we proposed this cluster, we pretty much had no idea what was going to happen, of course, but this was pretty much the diagram of the cluster, which was we wanted to investigate thermal performance, or just the idea of, we wanted to treat the concept of thermal measurements, and we wanted to do it in two different ways, one digital and the other one physical. And we knew that at some point, the intersection between the two will create some sort of uncertainty, and that intersection point is what we wanted to measure. And none of us were experts on this topic, but we knew that we could always go and consult to people who were experts on this topic. So the idea was more to introduce to the collaborators a problem that was very complex and that we were not experts on, but that we knew how to actually get submerged in. And we've already had done it in two previous clusters. One was the responsive acoustics cluster in Copenhagen, where we dealt with sound, and then the other one was the designing the dynamic in Melbourne, where we dealt with sailing. And this third one is pretty much about heating. We also kind of dealt with experts. We invited Philip Bidulp so that he explained to us the actual, let's say, the reality of the situation, so that we would actually at least get like a picture of how it all worked. But the idea of the cluster was that we wanted to make sure that everybody went through all the steps. We wanted them to actually go through a series of design, that they actually learn how to segment their models by using CFD software that created like voxels, that they could actually also simulate the software, and then they could also analyze it. Because we realize we've done a lot of FEM courses, and we've gone to a lot of conferences, and we've noticed that this is a very difficult subject. So we wanted to make sure that all the cluster collaborators would actually go through it and that they could take this knowledge with them. And this is pretty much the exhibition night, so we'll begin from the end. This is the exhibition night that was done yesterday, and on the bottom you can see that was exactly how it was proposed. And I'll hand it over to Camille, which is going to explain about how we did the actual physical measurements.
So one of the main experiment is looking on how we simulate the digital simulations on the physical boxes. So at the beginning we try to do some sketches of the boxes, and we have along the way we have a debate whether the boxes should be black or transparent. And then we end up with two boxes which have black using a thermal camera and 27 sensors of transparent box. And we're dealing with a small area where we have 300 by 300 boxes, size of boxes, so we can rotate the facade design when we designing the surface of the facades. So at the early beginnings of the physical testings, from the digital simulations, the collaborators were encouraged to design very simple facades, and from there they do a couple of simulations and do a looping process of a couple of design iterations. So we have here more than 25 type of facade designs, and we try to encourage the participant to actually engage both of from simulation to physical design stages. And we also test things in different thickness and the materials. It depends on how the collaborators asking the questions for the heating and cooling investigations of the facades. And for the physical simulations, this is how we set up the physical testings, where we're looking into the first boxes on the right side. We're looking to the a black box where we have a thermal camera inside the boxes and another thermal camera in front of the box. So this is the early observations, how the heat transfer from one point to another. And the collaborators will do a couple of iterations and to see the behavior of the heat transfer on different designs. And on the right side, we have a 27 sensor on transparent box. So we have 500 watts of lamp, and we try to see how the heat transfer from the facades into the spaces using a 500 watts of lamp. So, we do these things a couple of iterations, and then we look on the results of the simulation of physical. So I pass to Mani to explain more about the physical testings.
The physical testing is done in two parts. One part of the setup we designed back in Melbourne, Borderways Bus, which is the 27 sensors, the data protocols, but how we're actually analyzing the 27 sensors, which gave up something like 15,000 data points just for the 10 minutes. That's a challenge for us, but we're taking this with us to the cluster, and then we developed this system to analyze the data. So here is the three examples. One's the top empty box, the control system. I did the finger testing of every sensor, so you can see the temperature goes up with each of the colors. And then the middle one and the bottom one is two different facades. You can see the behavior is quite different. So the system worked. Then we taken the sensor data and coded in such a way that we can import it into the same visualization system that we're visualizing the digital simulation, which is PowerView. So the 27 sensors in linear and interpolated, and we can visualize them. I got a couple of videos to quickly show you. So this coding is done by MATLAB, which the size of the circles is the temperature difference. And this is the PowerView. You can see my fingers snaking around in the box. So this is this one. You can see the heat, because the facade is quite thick, it heats up the front much quicker than the back one. This facade is very thin and got gaps. And the heat just went right through, heated up the end back of the box instead of the front. And you can see the circles is much bigger than the other ones. But because the system was designed at the same time we designed the facade, so the facade design informed the process that we designed the sensor analysis system. And one thing we found is quite interesting part of this uncertainty idea is that we want to visualize the data quickly. And this part of coding took quite a long time. This didn't come through until the final day. But the MATLAB part was very quick and dirty. So maybe it's not as visually pleasing, but then we could get the direct feedback much quicker than in the second day we start looking at something is happening. Oh yeah, the facade is getting heated quicker, this one, that one's not so much quicker. So we had the thermal camera one, which is connecting the laptop, 5 minutes setup, and then that's running. And then the next stage is the MATLAB, took probably 1 or 2 days, and then this took about 3 or 4 days. And then also then when we come back and compare the results from this results from the physical testing to the digital testing, we found that there's some very interesting complexity issues. With digital testing, we know exactly what we're simulating. We're simulating CFD, and it's very deterministic. But with the sensor data, it's not even repeatable because room temperature will be different. The facade could have been heated before we put it in there. We even tried to spray the sensors down, and that changed the whole setup again because the sensor decided to heat up differently because the initial temperature is different. But then we're still able to get some sort of understanding. So the one thing that we learned from this is not what is better or what is good or bad, is what is useful and what is not so useful. And even this is not maybe accurate scientific, it's still quite informed design, which we think is quite good for this outcome of this cluster.
Okay, so we're just going to continue showing you the work that the participant did and show you with a little bit more detail. So this is EPEC's design. So you can see here the design, the broken FEA model, how you actually split it, because depending on your design, you have to split your FEA model differently. And we do that in Salome. And then upstairs here, you see the ParaView result done in ParaView and in Elmer. And then here you can see the actual thermal camera images. And then here's an example where EPEC also added thermal paint, and you can see how thermal paint works. This is another prototype by Aline, where she wanted to show curve folding, and the prototypes actually fold or let light in or out. And this is the actual model tested, the actual thermal images. And then her model was a little bit more complicated because it wasn't really like solid. So we had to actually only do it in 2D, the tests. So you see up there, we did that in Agros 2D, which is a 2D FEA solver. And then here's the comparisons from the thermal camera, the data, and then the cube visualization that Mani did. So it's actually pretty cool to see all the different 3 kind of stages of her design. This one is by Andrea, and she was looking more like curvy thicknesses, and you can see the image. And this one's by David Gerber, just visualizing curvature of fins and filtration. This one's by Raphael. He was looking at biological skins. We really won't see it here, but he did an actual physical one where he embedded moisture and it evaporates and cools the facade as we were measuring it. This one's by Jacob. He was investigating, he actually did a milled facade and then filtration as well. And this is Patrick. Some of them were actually not just doing heat analysis, but we're also trying to do convection by using Navier-Stokes and fluid dynamics. But it was a bit difficult to do in 4 days just to actually simulate these things. So a couple of them did it, a couple of them didn't do it, so depending on the complexity of the design. In this case, some of them did do CFD. This one's by Ryan, and he was also looking at fins that would capture air and then cool down the facade because of the curvature. But at the same time, I'll just show pretty much kind of like the type of analysis that he was doing in terms of heat. And you can see the results that were coming from from Elmer, the FEA analysis. And then one of the interesting things was also the different ways in which you can display this data. So we only kind of give them like a little introductory example of ParaView, but they actually figured out different ways in which they could display their data, and they actually kind of did this on their own. This one's by Shida, and she was looking at fold plates, and this was also a little bit difficult to simulate digitally, but what we did was we actually did physically the test, and then based on the intuitions that we built during the testing, we then went back to the CFD, and then we knew whether, if we got a bogus result from the CFD, we knew that it actually had to match a bit more like the physical one. And this one was by William, which also was an amazing red shirt. There was a white shirt, but that was very good. He was embedded in the cluster and did almost all the work throughout the cluster, and also had time to actually also do a prototype. And it was really cool because he investigated an actual sheet of an elastic film that had insulation inside, and then also got to go through all the phases, the physical, the digital, and the prototyping. And just to finish it, this is all of the collaborators and pretty much the team, except for Mark and Jane, which are sitting right there. And also we have back in Melbourne, Shen and Shu Yin, and also Ryan, Ian Ridley, and many other consultants that we had to work. And our cluster was also sponsored by Bentley, and we want to thank them for the support, and also thank you Smartgeometry for inviting us and giving us the opportunity. So pretty much, thank you.